So let's look at motion on a ramp. So what I'm going to imagine is a cart, and let's say it starts out here at t = 0, and it's moving up the ramp. So a second later, it could be here, and it's going to be slowing down because it's going up a ramp, and then it's going to be here at t = 2. And if I lay out a traditional coordinate system where x is horizontal and y is vertical, we could say that its x position changes with time from 0 to 2 to 3, and its y coordinate changes from 0 to 1 to 1.5. And so I can also make a table of that, showing that as time changes, the x and the y position change with time as well. So this would be two-dimensional motion, because it's moving in the x and it's moving in the y. But isn't the cart really just going forwards and backwards along a line? So to simplify the problem, what we do is we don't assign a traditional coordinate system. We take the coordinate system and we tilt it to match the motion. So we have the ramp that is still tilted, and we have the cart again at 0 seconds, 1 second, and 2 seconds. But this time I have tilted it so that the x-axis is lying along the surface of the ramp. And then the y-axis is going to represent any motion that's above the ramp surface, like if the cart was hopping up off the ramp, or maybe even if the cart crushed through the ramp and went below into the negative y coordinates. So for motion that stays along the surface of the ramp, the y coordinate is always 0. So all of the information is along the x-axis. That's one-dimensional motion. So I can make a table and see that anything interesting is only happening in the x. Nothing interesting is happening in the y. So we could use our kinematic equations for one-dimensional motion easily for this case. Just tilt your coordinate system. So let's go back to that example and say that we had a ramp, and let's have a cart, and let's say that it was starting with an initial speed, so somebody had pushed it up. And then it's going to coast up the ramp and slow down until it reaches a stop. Since it's slowing down, the acceleration has to be opposite of its speed. So while it's going up the ramp but slowing, the acceleration is down the ramp. Which to me makes sense because gravity is working in the direction down the ramp. Gravity is going to slow it down. So it coasts up and it comes to a stop for an instant. So for the instant that it's at rest, it doesn't stay at rest though, right? Gravity would eventually pull it left and speed it back up. So even though it's got a v of 0 right here, its velocity is still changing because it's still on a tilted ramp and gravity is still trying to pull it down. And then maybe let me redraw the ramp. So here it was at rest. And then sometime later, it would be coasting down the ramp. How about we call that VF? So during this time frame, it's going to be moving down the ramp, but speeding up. And since it's speeding up, the direction of the acceleration has to match the direction of the velocity here. So the acceleration is still down the ramp. That's still the direction that gravity is working on the cart. The acceleration of a cart along a ramp is going to be equal to plus or minus g sine theta. Where theta is going to be the angle of the ramp measured from the horizontal. So if it was a flat track, you would put in 0 degrees. In this case, the track looks like it might have been tilted 30 degrees above the horizontal, so you would just plug in a 30. G is our 9.8 meters per second squared, the free fall acceleration. The plus or minus basically means, is gravity trying to work in the direction of your coordinate system or against your coordinate system? So let's say that I had called this my positive x direction. So my positive x direction is kind of up and to the right, but my acceleration was down and to the left. The direction of this is opposite of this. So then we would choose minus. The acceleration is in the negative direction, so we would choose minus. Right. Another thing I should note, right, this acceleration equation only works when we're going to say that there's no air resistance and no noticeable friction. And also no other forces, like no other springs or strings or anything. It's really just the cart on a ramp and gravity. Let me play around with coordinate systems for a second to show you where that comes from. So let's say we have the ramp again. The angle of the ramp is measured from the horizontal. Here's the cart at some instant, and I don't really care if it's going up or down the ramp right now. If the ramp wasn't there at all, gravity would make it go into free fall with a free fall acceleration of g, pointing downwards. But the ramp prevents that from happening and makes the cart only move along this direction. So how about I assign a coordinate system then? Plus y and plus x. This acceleration vector that would happen in free fall then points in 2 dimensions. It points downwards kind of into the ramp, but it also points along the ramp surface. Right? So it's not just pointing purely in the y, it's also pointing a little bit to the x. So let's break it into components. So let's take a second and look at this bigger triangle here. This is theta. This down here is 90. So then doesn't this angle up here have to be 90 minus theta? Okay. So now let's remember that this is 90 minus theta right here, and look at this small red triangle that I drew. So this is 90 minus theta. This is 90 because it's parallel to my x and parallel to my y. So that means that this is also theta right here. So 90, 90 minus theta, and theta. This is a handy little trick to look at the triangle in a triangle that we'll probably use it quite a bit more in chapter 4 and 5. Right, so first you look at the big triangle, and you have theta here and 90. And then if you draw a component triangle in here, this is 90, so this becomes theta. So then this side of the triangle is going to be adjacent to the angle, so it would be the acceleration in the y. It would be plus or minus, and so in this case we'll choose minus because it's pulling down into the ramp, away from my plus y, minus g cos theta. And let's say if the ramp wasn't there, but the ramp blocks it. So then AY goes to 0. On this portion of the triangle is the opposite side. Now for this example, for this coordinate system, this part of the triangle is working leftwards, but my coordinate system is positive to the right, so I'm going to choose minus. The hypotenuse, which was G, times sine of the angle. All right, and so that's where that equation came from. The cart would be in free fall, but the ramp blocks part of it. And so what's left? What part of free fall can the ramp not block? This component of it, G sine theta. So let me try this example real quick. Let's imagine that we had a cart here initially, traveling up the ramp at 0.5 meters per second. And sometime later, it was still moving up the ramp, but slower at half its original speed, 0.25 meters per second. Let's set our x equals 0 here at the initial position and consider our positive x-axis to be in this direction. And the ramp is going to be tilted 45 degrees above the horizontal. How about we figure out the time interval between these two? So we could try this equation, and if it doesn't work, we'll try a different one. Let's try AX is equal to delta V over delta T. So we know delta V, we know the change in velocity. And we're looking for delta T, so we can use this equation if we know AX. And for these problems, we're going to assume that air resistance and friction aren't an issue until we get to Chapter 5. So in this case, we can just plug in plus or minus G sine theta. And for delta Vx, right, we're just going to do Vxf minus Vxi. So then if I have multiplied delta T up to the other side, I'll get plus or minus G sine theta times delta T is equal to Vxf minus Vxi. Should I choose the plus or minus here? My positive direction is up the ramp, but gravity is working down the ramp. So I'm going to choose minus. So then solving for delta T, Vxf minus Vxi divided by negative G sine theta. Vxf, the final velocity along the x direction, was 0.25 meters per second minus Vxi divided by negative G. All right, which gives me 0.0361, and the units would be meters per second from the numerator divided by meters per second squared in the denominator, but that's a fraction divided by a fraction, so let me invert this one and multiply it. 0.0361 meters per second times second squared per meter. Meters cancels out, one of the seconds cancels out, and then it looks like I wasn't very precise. I'm like 2 sig figs, 2 sig figs, 1 sig fig, so let me just do 1. So I'll round this to 0.04 seconds. What would the cart's velocity be after 2 more seconds? So that would be 2 more seconds after this. So I'm going to say t is equal to this value. The more precise value would be 2.0361 seconds. I used this number to keep going in the problem because I don't want to round to keep doing more math. I'm going to keep the extra digits do more math, and then round its final answer. So I could use this equation again. And this time I know AX and I know delta T, but I want to be solving for V final. So then multiplying the delta T up here. And the AX was negative G sine theta. And delta Vx is Vxf minus Vxi. So then to get Vxf by itself, I add Vxi to both sides. Now what do I want to call initial? I could use this as the initial, or this one. It doesn't matter. We get to pick one. Because that equation that I wrote down is good as long as the acceleration is constant. And the acceleration was constant from here to here, and from here to the stopping point and to turning around and coasting back down. So how about I just go ahead and pick this one as our initial point again. So then the delta t between the very beginning of the problem and this time frame that we're now looking at would be 2.0361 seconds times negative g times sine of the angle of the ramp plus the initial velocity. And the initial velocity here was 0.5 meters per second, and it was going in the positive direction. So I plug it in as positive, is equal to Vxf. So I get negative 13.61, and the units would be a second times a meter per second squared, which would be a meter per second for this whole term, which is good because we're adding it to another term that's meters per second, would be our Vxf. I'll round that to just 1 sig fig again, so that would be negative 10 meters per second. Now, let's be careful that we've introduced vectors and mentioned that there are certain quantities that are vectors and should have a direction. Velocity and acceleration and displacement are all vectors and they need a direction. So this answer of negative 10 meters per second, it is indicating a direction, but that's depending on your coordinate system. And your coordinate system might be different than my coordinate system. So as our final answer, how about we say 10 meters per second down the ramp? That way our velocity, which is a vector, has a magnitude and a very clear direction.